Now we come to part D, which asks us to evaluate the integral.
The function e to the power of 7x times sine x. And there are really a couple of ways that we could approach this. So now, is it an elementary integral? No, and there's no way to rewrite it as a combination of elementary integrals. U substitution doesn't really seem effective here either. E to the 7x is technically a composite function, of course, but simply letting u be equal to 7x doesn't really get us very far. Amongst our more sophisticated methods, it's not a rational function, so the method of partial fractions doesn't apply. It's got a trigonometric function in there, but also an exponential function, so our trigonometric strategies don't apply, and we don't have that radical form or anything that resembles that radical form that would indicate a trigonometric substitution, which brings us then to integration by parts. And because we've got a product here, that is often the situation where integration by parts is appropriate. But the reason I say we've got a couple of ways that we could approach this is because typically for integration by parts, the thing that we differentiate, what I call W, is ideally something that's going to get simpler when we differentiate it. But that's not true of either of these functions. E to the 7x just will differentiate to give us multiples of itself, and likewise sine x just differentiates to give us another trigonometric function. At the same time, neither of these is particularly difficult to integrate. So that means that we could really set up integration by parts here in one of two ways. We could differentiate the exponential function and integrate the trigonometric function, or we could differentiate the trigonometric function and integrate the exponential function, and in the end, both methods would be successful. So I'll do the first of them, but you could certainly follow the opposite approach, and there'd be absolutely nothing wrong with that. So we'll use integration by parts. With W, so we're going to differentiate e to the 7x, and dv then would be sine x dx. And I might be slightly more tempted to set things up this way anyhow, simply because I think it's slightly easier to apply the chain rule to differentiate e to the 7x than it would be to integrate it and wind up with fractions coming out of the integrals of e to the 7x. But again, it really doesn't matter. So dw then will be 7 times e to the 7x dx, and v, the antiderivative of sine x, is negative cosine x. So that tells us that our integral can be rewritten as v times w, so negative e to the 7x times cosine x, minus the integral of v dw, so minus the minus will become a plus, and I'll pull that 7 out as well, so that'll give us plus 7 times the integral of e to the 7x cosine x. Now, ideally with integration by parts at this stage, we would have an elementary integral, or at least an integral that was simpler than the one we started with. And that hasn't happened here. We started off with an integral that was an exponential function times a trigonometric function. We've still got an integral of an exponential function times a trigonometric function. And sometimes that can indicate that integration by parts, or at least the particular way that we've set it up, just isn't working out for us. But because things also haven't gotten worse, my advice is always in these situations to try one more application of integration by parts and see what happens. But when you do so, remember, you've always got to set up integration by parts for the second time in a manner that's consistent with how you set it up the first time. So in this case then, because we originally differentiated the exponential function and integrated the trigonometric function, we need to do that again the second time around. If we switch the roles, all we're going to do is undo our original use of parts and basically wind up right back where we started. So, we'll use integration by parts again. And so we're still going to let w be e to the 7x. That part hasn't changed. But dv will now be cosine x dx. So dw is still 7 times e to the 7x. And v, an antiderivative of cosine x, of course, is sine x. So now we've got that our original integral is going to be equal to negative e to the 7x cosine x plus 7 times. So we're applying integration by parts now to this integral. So again, that's v times w, e to the 7x times sine x, minus the integral of v dw. And I'll pull that 7 out. So that'll be minus 7 times the integral of e to the 7x sine x. And so then we can multiply this through. So that'll be negative e to the 7x cosine x plus 7 times e to the 7x sine x minus 49 times the integral of e to the 7x sine x. And while that still hasn't gotten any better, that is a significant integral because, in fact, that's our original integral. This is one of those cases where the integral that we started with reoccurs through the use of integration by parts multiple times, which effectively means that we can solve for it. So if we've got 49 of them being subtracted on the right-hand side, we can add 49 of them to the left-hand side. So then 50 times the integral of e to the 7x sine x is going to be equal to negative e to the 7x cosine x plus 7 times e to the 7x sine x. And therefore, the thing that we're actually after, which is that integral on its own, we'll get it by dividing through by 50. So that tells us that the integral of e to the 7x sine x is negative 1 over 50 times e to the 7x cosine x plus 7 over 50 times e to the 7x sine x. Now we need to remember to include our constant of integration. Again, if you set up integration by parts initially the other way around, you would wind up with the exact same expression here in the end. It would just be the details of what would come out of integration by parts at each stage that would be a little bit different with the opposite setup. But nothing wrong with doing it that way either. Again, you'll wind up with the same answer.